throughout math and science is a formula. A formula. And what's special about a formula is it's an equation that never changes for the most part. An equation that never changes. So you're going to use it, the same formula, over and over and over and over again. And it's something that you could probably use. I use it every day because Sophie lives in the Eastern time zone, and I live in Central time zone. So I can say that Sophie's time is equal to my time plus 1. As silly as that is, that's a formula. Okay?
Okay.
It's never going to change. Whenever I want to know what time it is, well, it could change if maybe you lived in a place with no... If you moved, it would change. Or, but for the most part, it's going to stay the same. A big one that a lot of people are seeing now, especially with world geography and world internet, is temperature. And these, as far as I know, will never change. I don't know if the boiling point of water could ever change, but it hasn't changed in thousands of years that we've been on the planet, and that's where the Fahrenheit and centigrade temperatures come from. So the Celsius temperature, the temperature in Celsius is equal to, and I know this has a fraction, I'm not going to do any examples, I just want to show what formulas look like.
Okay.
Because I haven't taught you how to do fractions yet, and I don't want to say that, oh yeah, I don't know how to do fractions, but I want to try to do, I want to try to be like progressional about this. And that's a scary looking formula. But in the next section, you're going to say, oh, that ain't so scary. So in other words, this is the temperature in the United States. If I want to know the temperature in Canada, then I would use this formula. And it works backwards too. And we will probably solve it backwards someday. But if I know the temperature in Canada and I want to know what the temperature even though they're the same temperature, they're just different numbers, you would do 9/5. Notice the fraction's upside down when you go backwards. And it's not going to be minus 32, it's going to be plus 32. Because they're inverses of each other. So these are just examples of formulas. And I just wanted to bring those out because I don't want to do any specific examples with formulas right now because we haven't really taught any kind of computational methods. That's going to change. In the next section, we're going to start doing computational methods. I just wanted to throw out some examples of formulas. And mainly because they're used everywhere. This one's a big one in chemistry. Did you ever take chemistry?
No.
Oh, so you would know what this is. This is a very important formula.
Okay.
It relates the pressure and volume of a gas to the number of molecules. R is a constant, and the temperature. So pretty much it says that this number is pretty much a constant. They're not going to change. So this pretty much relates pressure and volume to temperature. It says they're related. This is a huge discovery, and mainly because when you think of temperature, for this to be related, you could have zero pressure, you could have zero volume, but this also proves that what? You can have zero temperature, and I don't mean 0 degrees. I mean no temperature. If you couldn't have no temperature, this formula couldn't be possible. This was huge. And there is an absolute 0. And I think it's minus 243 degrees Celsius. I think that's what it is. I could be wrong. And what this means, at this temperature, absolute 0, temperature is measured by the speed of molecules. And it is so cold at this temperature that molecules are unable to move. That's how cold it is. And there's a big difference between 243 and negative 243.1. I mean, It's huge. Because molecules move at this temperature, they don't at this one. And it increasingly, as you gradually get higher and higher and higher, the significance gets drastically smaller. Like, there isn't a huge difference between, I mean, we could feel the difference between 90 degrees Fahrenheit and 30 degrees Fahrenheit. You can feel the difference. But there's that much bigger a difference between this temperature and this temperature just because it's so close to absolute zero. You're talking about like the temperature at Pluto, where there's less and less and less and less heat, But then again, it's not just the heat factor, because heat isn't the only thing that moves molecules. Gravity does too. So there's other gravities out there too. And the gravity and that's why all the crazy planets that they're discovering and pieces that are outside of Pluto and have these crazy orbits, and just a whole fascinating. The solar system has changed after the year 2000 than it was when me and Sophie were in high school, because I don't know. When I went to school, I was taught that Pluto was a planet, and now Pluto is not a planet. So
I think they made it a planet again. I think they brought him back into.
Yeah, it's not. They got a special word for it. It's not a full planet. It's like it has to take the handicap ramp. It's not. So anyway, these are formulas, and they are used. The same rules apply to algebra, to these formulas, but when you take chemistry or when you take physics, the algebra might not be explained as well. So I just want to kind of cover those kind of examples in these classes. And that ends the first topic, the first section.